Hello, and this video is designed to go through Bayes' rule. Bayes' rule and conditional probability, which are sections 3.7 and 3.5 respectively, are going to be pretty important, and they kind of go together. So first of all, I want to talk about what Bayes' rule actually says. So let me just go to OneNote here for a minute. So when we're looking at Bayes' rule, we have in our mind two different events that we're looking at. And people call it Bayes' rule or Bayes' formula. I'm going to call this equation 1. And Bayes' rule says that the probability that the event A occurs, given that we already know B occurs, is equal to this following ratio. It's the probability that A and B both occur divided by the probability that B occurred. All right. And we talked about this in class, what this means as far as a Venn diagram. So there's a couple of kind of useful things to know about Bayes' rule. So first, it's kind of useful to have a picture of what's going on. What we have in our mind is that this is going to be our sample space, and this is some event B. In fact, let me redraw this as a square. And I'm going to assume that the area of B is proportional to the probability. So this whole sample space has an area of 1, and maybe B has some area, maybe, it looks like 0.4 or something like that, 0.3, right? Okay, and then we have the event A. So the event A is going to overlap it. And what we're saying with conditional probabilities is we're saying that we know A occurred. So we're saying that we know we're in this sample space, we're in this portion of the sample space right here, we're in B. So this is what the given B means. It means that we know we're in here. And the conditional probability here is just looking at the probability that A is in B. We're looking at the percentage of B that also has A occurring. And that's what a conditional probability is. So it's the ratio of this yellow area to, let me draw it a little bit differently. This little portion here, right? So this is the percentage of times that A occurs when B occurs. And that's a conditional probability. But Bayes' rule says that this is how we compute this. And this is the reason why it works, right? It's the probability of the overlap divided by the probability that I'm in B. And then, in fact, that should be the probability that A occurs given that B occurs. So it's kind of important to understand this from a Venn diagram. We also understand this when we look at a table. So, for example, if we go to the notes, we had some examples where we were using tables. Let me look at one rather quickly here. Let's see. I think I gave some in class, perhaps. I can make up one here. Let's just suppose, for example, we're looking at whether or not a person smokes and whether or not they have lung cancer. Okay. So we'll have here that a person is a non-smoker or a smoker. And this will be whether or not they have lung cancer. So I'll put a little plus, meaning that they have cancer. And by cancer, I mean lung cancer. And a minus that they don't. Okay? And if you look at these numbers, you can find this data online. It's kind of interesting. But here is here's just some numbers that I'm going to make up. Okay. And so if you look at this, you notice that there are a lot more non-smokers that get cancer than smokers. But the reason why is because there's a lot more non-smokers. So what am I interested in computing here? Well, I'm interested in computing the probability that you have cancer given that you smoke. Okay, given that you're a smoker. And so when we say that we're given the person's a smoker, what that means is we already know we're in the first column. So it means that given they're a smoker means that we're only looking at these individuals. This becomes like our event B, right? And so I'm looking at the percentage of smokers that get lung cancer. And so if I go ahead and compute that, that's rather easy, right? That's going to be equal to, well, I have 800 people that are both smokers and have cancer divided by 1,000 people that are smokers. So it's 80%. And this is the reason conditional probabilities figure very largely in medicine. This is why when you go to a doctor's office, he asks you all these questions. Do you drink? Do you smoke? Do you do this? Do you do that? Not because they're nosy, but it's just because this sort of differential diagnosis is possible when I have this sort of information. If you come in with a cough, should the doctor worry whether or not you have lung cancer? Well, if you're a non-smoker, probably not. Okay? If you're a smoker, yes, probably. Okay? And by the way, these numbers are probably way off, right? I mean, this is probably more like, and I forget the exact numbers. I used to kind of keep on up on medical statistics a little bit more. They're probably a little more like this, okay? So anyhow, but this is the idea. The fact that if I know you're a smoker, given that you're a smoker, I can estimate that your probability of getting cancer is a lot larger. So I might have to take that seriously. Okay, so this is what the conditional probability means, and this is how Bayes' law figures into it. One of the things we use Bayes' rule for a lot is where we're computing probabilities of intersections. So an important use for Bayes' rule is that if we're given conditional probabilities, we can compute probabilities of intersections, right? So the idea here is that I can compute the probability of A intersection B just using this formula, right? If I multiply both sides by probability of B, and let me add, I'm gonna actually make two versions of this formula here, okay? I'm gonna make the probability of A given B, that'll be equation 1A, and I'll also make the probability of B given A. And of course, this will be exactly the same in the numerator. The intersection doesn't care which way you take the intersection, but I'm going to divide by the probability of A. All right. So applications of Bayes' rule, there's three applications. The first is we can compute probabilities of intersections. So I'll say uses of Bayes' rule to compute probabilities of intersections. Probabilities of intersections. So it follows from 1A. If I multiply both sides of equation 1A by the probability of B, I see something kind of interesting. I get this formula here. The probability of A intersection B is equal to the probability of A given B times the probability of B. And I like writing it this way because it really kind of illustrates why this rule works. Because one way of saying the probability that A and B both occur is to say it's equal to the probability that B occurs first, that's this part, times the probability that A occurs given that B occurs. So it makes it really kind of a nice way to interpret these things. If I go to equation 1B and multiply by the probability of A, notice that I get a second formula for the probability of the intersection. I get this. So notice I have two ways to compute the probability of A intersection B, which is kind of nice. So I want to do a few quick homework problems to kind of illustrate this, okay? So here's a homework problem that's kind of nice. It says, suppose these two events, B1 and B2, are mutually exclusive and complementary, and all that means is they just basically, they're complements of each other. And now we have another event, A, such that the probability of A given B1 is 0.3. Of course, in your homework, it'll be a little different. And I'm doing the first problem, by the way. And the probability that A given B2 is equal to 0.6. And now I want to find the probability of B1 given A. Okay? So I can do that. So let's look at what we have here. So in this example, oh, come on. Okay. So in this example, okay, I'm given that the probability of B1 is equal to the probability of B2 is equal to, let's go back real quick, 0.24, 0.76. Okay. And I'm also given the conditional probabilities. So I'm told that A given B1 is 0.3 and A given B2 is 0.6. And probability of A given B2, what do we say, 0.6? Yeah, okay, 0.6. And now I want to know what is the probability of A and B1. And notice I can just use these two pieces of information and this formula I have right here. Okay. So I know that it's the probability of A given B1 times the probability of B1. And I can just go ahead and put that in, and when I do, I'm going to get 0.072. Okay. This is just going to be 0.24, right? That's this number here. 0.24 times 0.3. Okay. And when you do that, you'll get 0.072. That's your final answer. Okay. And the probability of B2 given A1. So this is an interesting question. This is where Bayes' rule really comes in handy, okay? So I want the probability of B2 given A. All right. So the probability of B2 given A. Well, let's just go from the definition, right? So if we go back to the definition, go back to equation 1A or 1B, we'll see this is the probability of B2 intersection A times the probability of A. Now notice I don't know how to get the probability of A, but I do know that A either has to lie in B1 or B2. So I can get the numerator, okay, because I can use my conditional probability formula to get the numerator. That's not too bad. But the probability of A is not so obvious. And what I'm going to do is I'm going to realize that B1 and B2 are complements. Okay, so we think of B1 and B2 like this. So if I think about A, the probability of A occurring is the probability that either A is in B1 or A is in B2. So I can write the probability of A is equal to the probability that A is in B1 plus the probability that A is in B2. And I can get each of these intersections, again, using Bayes' formula, right? This is the probability of A given B1 times the probability of B1 plus the probability A given B2 times the probability of B2. And I can substitute this in. If I put this up in here, I end up getting my final answer. At least I get the form that I'm going to use, and then I'm just going to substitute the numbers in, okay? So we said this is the probability of A given B2 times the probability of B2. And then down here, A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2. And now I can go back in and substitute these numbers, right? I know what all these numbers are. So I know that this is equal to, we said this was 0.6 times 0.76. And of course I'm going to have this same term down here also, so I'll just put it down here. Okay? And then we had 0.24 and 0.3 down here. We did that calculation earlier. Okay? And if you calculate all this out, right, so we have 6 times 76, 0.456. So I have 0.456 over, and on the bottom we figured out earlier this was 0.072, 0.456, right? So we have 0.456 over 0.528. Let me write this a little better. And now we can go ahead and just figure out whatever that is. Just put that in our calculator, and when we do that, our calculator, and 0.456 divided by 0.528, oops, 0.528, and I roughly get about 87%. Usually we write probabilities out to 4 decimal places, so I'll write it like this. And that's my answer. So these sorts of problems are kind of fun to work once you get the hang of it. Okay, but that's one of the ways that we use Bayes' rule. And this way comes up a lot when we're talking about medicine. So we talked about this thing called false positives and false negatives. And so I want to go through this a little bit. So when we think about, and so another application is looking at false positives and false negatives. In other words, we use Bayes' rule a lot when we're doing testing. And so like we mentioned in class, testing is a very general term. You could be testing for a variety of things. You could be testing for a drug like cancer. You could be testing for some sort of drug that's in a person's system. You could be testing for a part to be defective, like we did with the O-rings. There's all sorts of testing, okay? But what we do is we think of testing in 2 ways. We think of us as knowing reality, okay? So one of the things we're going to talk about is that the person has the condition, okay? So we're going to call plus C the event that a person has the condition. They're positive for the condition, okay? And the other is that they don't have the condition. So this is reality. And then we're going to look at the results of the test, right? So we can have 2 outcomes. We can have a positive test or a negative test. In other words, the test comes back positive for, whatever we're testing for, right? Or it comes back negative. Now, normally what you're given is you're given a conditional probability about what the test will reveal given that the person has the condition or doesn't have the condition, okay? And so the way this works is usually when we're talking about testing, especially medical testing, we have 2 types of tests. We have one test that has an incredibly high degree of reliability. That's called the gold standard. However, very often these sorts of tests are very expensive. So drug companies and people like this, they'll make, and people like this, corporations are people, right? Anyhow, drug corporations and entities of that sort, they will create a cheaper version of the test. They can test more people, screen them in a way, but they aren't as reliable. How do they know how well that second test works? Well, they use people they've already tested with the gold standard, so they know whether or not they have a condition, okay? So we talk about this thing called a false positive. And a false positive is when you have a positive, but it's not true. So in other words, this is when you have a positive test given that the person doesn't have the condition, okay? So if I want to talk about the probability of a false positive, it's this conditional probability. See, this is a false positive. It's a positive test, but it's false, meaning it's wrong, because we know the person doesn't have the condition. So this is the probability of a false positive. So in other words, what happens is the person comes back and the individual testing them says, hey, you have this condition, okay? But they don't. So sometimes people call this false alarm, because we're saying that something significant happened when it didn't. Okay, the test is saying, something happened, but the reality is nothing happened. The person didn't have the condition. Now we also have the probability of a false negative, and as you might imagine, it's really the same sort of thing, right? It's the probability that we have a negative test, but it's false. In other words, the person really does have the condition. And sometimes people call this misdetection. In other words, something really happened, the person had the condition, but you missed it. Your test came back negative. And I believe I said this in class, but I'll just emphasize this again, that people generally talk about false positives, but false negatives are actually incredibly important, and they're rather insidious. If you think about a test for cancer, okay, I would much rather have a false positive than a false negative. A false positive, the doctor would come back and say, oh, you have cancer. And then, of course, I'd get all worried and upset for a short period of time, but then they would go back and use the gold standard and find out I didn't, right? And I'd be okay. A false negative, what happens is the test comes back negative. The doctor says, oh, you're fine, go home, don't worry. When you really do have the condition, you really do have cancer. And then, of course, by the time they figure that out, it may be too late. So false negatives are actually very, very important when you're talking about a serious disease. Okay, so how can we use this information, okay? And I want to go back to this problem that we talked about in class to kind of illustrate how this works. So we talked about a problem with an AIDS test, I believe. Let's see if I can find it here. Yep. So here we're talking about a test for HIV AIDS, and we said the probability that a person has HIV is 0.01. The diagnostic test can detect the virus with a probability of 0.98. Given that the chance of a false positive is 6%, what is the probability that a person who has already tested positive really has AIDS? Okay, so let's break this down in the beginning, okay? So the probability that a patient has HIV, that's telling me the probability that the person has the condition. So what I know from this is I know in the AIDS example, the probability that the person has the condition is 0.001. Now, it goes on to say that the test can detect the virus with a probability of 0.98. So if we think about what that means for a second, it means that if the person has it, the probability it comes back with a positive test is 0.98. In other words, this is the probability of a true positive. Okay, the probability that if the virus is there, it detects it. In other words, it comes back with a positive test is 0.98. And finally, we're told the probability of a false positive is 6%. Okay, so let's break this down. The probability of a false positive. So this means you have a positive test, but the person didn't have the condition, and that's 0.06. Okay. So this is what we're given. And of course, the obvious question we want to ask is, what is the probability that a person has the condition, that is, to have AIDS, given that they have a positive test, right? That's what we want to figure out. So what I'm going to do is I'm going to use Bayes' formula, and here's what Bayes' formula says, and I'm going to start just from first principles, okay? So it's the probability that we have AIDS given we have a positive test. So this is the probability that both occur. Okay. Divided by the probability a person has a positive test. I know neither of these, but I can figure out both from Bayes' formula. So if I look at the numerator, I know that I can use Bayes' formula. In other words, I can use formulas 2.2a or 2b. And what I'm going to do is I'm going to rewrite this a different way. I'm going to write this like this. Notice what Bayes' formula will let me do. It lets me rewrite the intersection in terms of conditional probabilities where I've switched the order. And I want that because notice that everything I know about is when the person has the disease. Okay? And likewise, I can actually re-express the probability that a person has a positive test because I know that person, they either have a positive test and they have the condition, or they have a positive test, and they don't have the condition. And again, I can rewrite each of these intersections using Bayes' formula. So it's important to understand this is one of the major uses of Bayes' formula. But again, I'm going to write the conditional probability where the condition of the person is what I know. Okay? Probability test positive, given they don't have the condition. Okay. And now I can substitute both of these back in. And I can just put the given numbers. So I know that my final answer here, so I'm going to use this for the numerator. And this is what I got for the denominator. And so now I'm going to say that the conditional probability that a person has the condition given they tested positive. And now I'm going to put my numbers in, okay? So I know the probability that a person has a positive test given they have the disease is 0.98. The probability the person has the condition, of course, is 0.001. And of course, this is the same thing in the denominator here. And then the probability of a false positive, which is the probability of a positive test given they don't have the condition, is 0.06, times the probability they don't have the condition is going to be 0.999. And if you go ahead and compute this out, you'll find something really interesting. This probability is roughly equal to this. Notice that this is less than 2%. This is very surprising, I think, to most people. That it says that if you have a positive AIDS test, the probability that you really have AIDS is less than 2%. Now I'll comment on something in real life, okay? In real life, this number is a lot higher. It's important to understand that, okay? And actually, these probabilities, this might be correct for the probability of AIDS, but I know with the test that they use now, even a couple years ago, the probability of a true positive was actually much, much higher. So this result isn't quite as impressive when you use more realistic numbers. It's higher. Right off the top of my head, I don't remember. I'd have to look. In fact, let me just do that because it's kind of fun. And I just used something that I found in the book, but it is kind of interesting to know what the actual answer is. Let's say probability to have is positive test. Let's see. Well, not so easy to find. I have to do a little more digging. Anyhow, I have to look it up, but I know it's definitely higher than 2%. This number is kind of a little too low to be realistic. But what it does mean is that, that in general, just because you have a positive test does not mean you have the condition. And very often the likelihood is low, but just not as low as 2%. That's all I really want to say. Let me do one last homework problem here. Some of these are kind of similar. I'll do one from 3-9. Oh, let's see. I can do 3.651. Let's just try that. So it says that we have independent events. It's important to know what independent events means. It means that the probabilities multiply, okay? And this is the third application of Bayes' formula, by the way. So we have two independent events. The probability that A occurs is 0.4. The probability that B occurs is 0.5. So this is problem 3.6.5 now. Okay. And we want to find the probability of the intersection and the conditional probabilities in the union, okay? So we also know that A and B are independent, so this is important. It's an important piece of information because for part A, we know that if we have two independent events, the probability of the intersection is the probability of their, the product of their probabilities. This is only true if they're independent. Okay, so because they're independent, I know that this is true. This is called the multiplication rule in the book. Okay, and of course I can put the numbers in right, and I'll just get 0.2. All right. Now, the next thing they want is they want the probability of A given B, and this is easy because another rule for independence. So this is a test for independence. But another thing about independent events is that the probability of an event is the same as its conditional probability. So this is a consequence of independence. Okay? In other words, if you think about it, it says that the probability that A is going to occur given that B occurs is exactly the same as if probability that A occurs if I didn't have any information. I want to show you why this is true. Here's what it's actually saying. Suppose this is a sample space. I'm going to make up an artificial example here. And suppose B, the probability of B was 1/3. Okay, so it's roughly 1/3 the sample space, all right? And I'm looking at an event A. And the probability of A occurs is, we'll say it's let's see, maybe 1/6. But I'm going to draw it like this. So the probability of A is 1/6. In other words, A takes up 1/6 of the sample space. Okay? And I'm going to have to redraw this to kind of show what I want. All right. All right. So this means that 1 out of 6 of the elements in S are in A. What it means to be independent, for A and B to be independent, is it means that this area right here is 1/6 of the yellow area. In other words, if I look at the elements of B, 1/6 of them are A. In other words, B looks just like the sample space to A. If I'm in B, there's 1/6 of A in here. In other words, 1/6 of the population of B is in A. If I look at the sample space, 1/6 of the population of S is in A. So this is what this formula means essentially. This is a good diagram to look at and think about. Okay, last question, what is the probability of the union? Well, here I'm going to use my general formula. Okay, so I know that the general formula for a union is equal to the probability of A plus the probability of B minus the probability of the intersection. But because these are independent, I can write these as the product of their probabilities. Minus the probability of A times the probability of B. And you could just plug those numbers in now. It's very, very straightforward, right? 0.4 plus, what is it, 0.5. And we've already done this, 0.2. So it's 0.7. Okay. All right, that's pretty good for conditional probabilities and Bayes formula. You want to think about the three different ways that we use Bayes formula. We use it to calculate conditional probabilities, calculate intersections. We use it a lot in testing, and we also use it when we want to. What was the last thing I said? Oh, when I want to look at independence also. This is another way of establishing independence, and this is what I say in the notes. Actually, I think it's not in this set. It's actually in the set of notes from 3.5. So that's important to look at. Okay, that's pretty much all on Bayes rule. And if you have any questions, of course, feel free to ask.